Okay, so here we go. As you prepare for this test, let's start at the beginning. You have two calculations of Q. You have Q equals MC delta T, and then you have Q either equaling mass times the latent heat of fusion, or you have mass times the latent heat of vaporization. Okay? Now, here's what's going to happen. I promise you, you're going to have a problem like this. I'm going to give you something like, okay, hey, here's a chart of temperature and energy, right? And here's the most important thing that you have to understand. When you dump energy into a system, it's going to do one of two things. It's either going to increase the kinetic energy, meaning that you're going to increase the temperature, or that energy is going to go to break bonds. Okay? Those are the only two games in town. So if the energy is increasing kinetic energy, you'll see the temperature goes up. If you see that it's breaking bonds, then you're going to see a phase change. Now, the opposite is true. Is if you remove energy, then that removal of energy is going to do one of two things. It's either going to make the particles slow down and decrease the kinetic energy, or you're going to form bonds. Okay? That's it. There is nothing in between. So if I ask you, is it possible to dump energy into a system and not change the temperature? Is that true? Yes. Yes. As long as that energy goes to do what? Break bonds. Or if I say, is it possible to remove energy but yet maintain a constant temperature?
Yes.
Yes, as long as you're removing the energy to form bonds. Okay? So just because energy is flowing in or out doesn't necessarily mean that you're changing the temperature, which is what allows you to boil water and make macaroni and cheese. Okay? No, that's to make electricity. Different. Okay, so let's say, hold on. Okay. So let's say that you've got some ice that's at minus 10 degrees Celsius. Okay? And you want to melt it. So it's the first thing that you have to do.
Zero.
No. What do you have to get the temperature to? Zero. So you're going to go from minus 10, right, up to 0 degrees. True?
Sure.
Minus 10 up to 0. When you change the temperature, what are you fundamentally changing? Rhymes with kinetic energy. The kinetic energy. Okay? That's what you're doing. You're giving a room full of Timmies a shot of hot cocoa. Okay? Here, Timmy, hot cocoa with little marshmallows in it. Timmy flips out, okay? Because Timmy likes little marshmallows. Right? So these Timmies are going to start to vibrate more. Now, they're still a solid. Okay? They're still a solid. But they're vibrating some more. They're not breaking loose, but they're getting close. So at this point, is there a temperature change?
Yes.
Yes, so what are you going to use? You're going to equals Q equals MC delta T. Now, are you going to use the specific heat of liquid water? No, what are you going to use?
Ice.
The specific heat of ice. Okay, because it's not liquid water, it's ice. Yeah, change the temperature 10 degrees, whatever the mass is, easy peasy. Right? Okay. Now, at that point, now we're going to continue to add energy, but now we're going to break bonds. Okay? So, if any of you, I'm guessing, at any given day, probably drink something that has ice in it. What's the function of the ice?
Cold.
By doing what?
Taking energy away from the water.
Beautiful. The function of the ice is to act like an energy sponge. Okay? It takes thermal energy from the water. Now that energy has to go somewhere. And that energy goes to break the bonds that hold the ice together. Which is why after a while, what happens to the amount of ice? It goes away because you've taken that energy and you broke the bonds. Cameo appearance by one of your classmates. Okay.
What's this video for?
Now, when you have a phase change, when you're melting something, are you going to use latent heat of fusion or latent heat of vaporization? Fusion. Because when you fuse stuff together, what are you doing? Yes, you're making it a solid, right?
When you're melting something?
Or freezing.
Or freezing.
Okay? So this is a phase change involving solids. This is a phase change involving liquids to gases. So this is solids to liquids, this is liquids to gases. Hence fusion versus vaporization. Okay? And yes, you will have the chart with all of that information on it. You just have to know how to use it. Okay. So at this point, we're going to warm up the water. That's going to take a certain amount of energy. Then we're going to melt it, and then we're going to use Q equals M times the latent heat of fusion. Now, what are the units for latent heat of fusion? Joules per kilogram. Now, what are the units for specific heat, though? Joules per kilogram, degrees Celsius. Why don't you think we have degrees Celsius on latent heat of fusion or latent heat of vaporization? Because the temperature doesn't change. Because what's the energy doing?
Breaking bond.
Breaking bonds. Okay? Or you're forming bonds and it's releasing energy. Okay? So then, you're going to warm up the water. Then what are you going to use? Are you changing the temperature?
Yes.
Yeah, mass delta T C sub P. Then you could boil it, and then you'd use latent heat of vaporization, and then you could warm up the steam, use the steam to turn a turbine. The turbine spins a generator. I can make toast.
Wow.
Okay?
In the bathtub.
Yes. So here's the deal. You have to know the critical points, and I'm not going to ask you something weird, okay, like iron, like the latent heat of fusion of iron. It's going to be water. Here's the deal. I'm going to start with, here's how this is going to play out. I might start with liquid water at, say, 20 degrees, and say, what's the total energy to take the water, boil it, and then warm the steam to 120, okay? Or I might say, here's ice at minus 10. How much energy does it take to take the ice at minus 10 and warm it to water at 20 degrees? Okay? So, anytime you have a phase change, and it's going to be water, I'm not going to do anything weird. The two temperatures you have to remember are what? 0 and 100. Okay? There. Got it? Good. Now, here's where the big question is going to be. And I mean a big question. Big question. So let's say this is 0.05 cubic meters, and let's say this is like 0.01 cubic meters, okay? And I'm going to start here, okay? So here's what's going to happen. I'm going to give you a pressure volume graph. I'm going to have everything labeled, and I'm going to give you a particular pressure and a particular volume. And I'm going to tell you straight up, here's the first thing I'm going to ask you to find is the temperature in Kelvin. Okay? And I'm going to give you the number of moles. And on the test, this is going to be the most big complex problem you're going to have on the entire test. And the first question is going to be to find that temperature. And this is the only time I would do this throughout the entire year. On the test, you can ask me, hey, Burkamp, is this temperature right? And I will tell you if it's right or wrong. Okay? That's going to be in the instructions on the test. I will tell you if you're right or wrong. Because if you start off with the wrong initial temperature, everything that you do on that entire problem is going to be wrong. Okay? So the very first question on the big gas law problem, I will tell you, ask me if this is right. Take advantage of it. You don't get docked points. And if you don't ask me and your answer is wrong, I will have no mercy on your soul whatsoever when I grade that part of it. Okay? It's a gift. Accept it. Right? So what can I do with this pressure and volume? What's one thing I could do with it? Keep in mind I've got a whole bunch of stuff over here, not much room over here. So I'm going to do something to shift it over there. I want to decrease the volume. So what's one thing that I could do? Well, I can increase the pressure, right? So if I increase the pressure, what would this do? If all I did was increase the pressure, what would it do? It would go up. And that would be an isometric or isovolumetric because I'm keeping the same volume. Okay? But I don't want to do that because I want to get that volume to 0.01. So what's another thing that I could do? I could change the temperature or leave the temperature the same because there's a big difference. Keep the temperature the same, change the temperature. What do you want to do?
Change it.
Let's keep it.
Yeah.
Okay? So let's say that the temperature is 300 Kelvin, just to make up a number. Okay? So if I want this to be an isothermal process, I want to end up from going 0.05 cubic meters, I want to end up at 0.01 cubic meters. So if it's an isothermal compression, what's that line going to look like going from here to here?
Pretty.
Like that.
Like that?
Like that.
Okay?
Hey, that's pretty
That's
good.
not a straight line.
You're right.
Because it's an inverse relationship because PV equals nRT. Now, so when I get to this point, what's the temperature? It's the exact same. It's still 300 Kelvin. But what's happened to my volume? My volume has gotten smaller,
So you have more pressure.
so I have
More pressure.
more pressure. Okay, nice.
It's like behind you.
So, what do we call this line then? Isothermal.
Because what?
I refuse to answer that.
It's a legitimate question. Why?
Permission to
Because
answer.
the temperature didn't change.
Okay,
Okay. That's all you have to say. Don't say anything.
now, is work being done?
No. I'm gonna plead with that.
Yes.
Yes. Is the volume changing? Yes. Anytime the volume changes, guess what?
There's a word.
Work is being done. Okay? So, here's the deal. When you have a curved line like this, and this is the one equation that is not on your equation sheet, but if you need it, I will give it to you on the test. When you have a curved line like this, you're going to use work equals nRT times the natural log of volume initial over volume final. Okay? Now, here's the deal. What's n going to represent? Number of moles, right? Is that ever going to be a negative number?
Probably not.
No.
No.
What's R?
It's constant value.
Gas law constant, 8.314 joules per mole Kelvin. Because we're in the Kelvin scale, the temperature is never going to be negative or zero. So I got my temperature at 300. I would have to give you the number of moles. Okay, I will tell you it's 0.01, it's whatever, how many moles there are. And you got this. But that isn't the point of the equation. Let's look at this natural log. In this case, my initial volume, I'm taking the initial volume of 0.05 cubic meters and divided by 0.01 cubic meters. Okay? Here's the whole point of this. So, basically, if you go through this, you're taking the natural log of 5. So here's what's most important. When I take the natural log of 5, is the natural log of 5 going to be a positive number or a negative number? Positive. Okay? Anytime you take the natural log of a number bigger than 1, you always get a positive number. If you take the natural log of a value less than 1, you always get a negative number. So as soon as I look at this and go that my initial volume is bigger than my final volume, I know that I'm going to have positive work. So why do I have positive work being done? The volume is getting
Small.
which means work is being done on the system. Okay? So what's happening is that I am pushing down on the plunger. Okay? Now, here's the deal. So if you physically look at what's going on, okay? So I'm up here. I'm going to do work, and I'm going to push down, and I'm going to make the volume smaller and smaller and smaller. Right? Volume's becoming smaller. What's happening to the pressure? It's going up, right? But what's happening to the temperature? Nothing. So what's happening is that even though I'm doing work on it, what's happening is that the thermal energy is escaping out because the temperature isn't changing. So here's what's important. All I know is that for now, all I care about is that this is going to be a positive number. Okay? I don't care what the number is. I honestly do not care what the number is. I just know it's a positive number. Now, at this point, I know that delta U is going to equal 0. Why? No change in temperature, right? So I've got a little thermometer in there, and I'm measuring this, and there's no fluctuation in the temperature. Now, delta U also equals Q plus W. Okay? So my Q is going to be this positive number, which means my W is going to be this positive number, which means my Q is going to be
Same number but negative.
same number but negative. Now, why does it make sense that the Q has to be a negative number?
This work has to be positive.
Okay? So basically what's happening is this. Anytime you compress a gas, the temperature wants to go up. Okay? Because particles don't like being compressed. They like to say, back off me, I need my space. Show up, big man. So when you do this, the little particles of nitrogen and oxygen are going, whoa, this is bad. Okay? And they all get worked up into a dither, and on an atomic level, it's just bad. Okay? It's like freshmen, you know, and we've taken away their cell phones or something. It's just bad.
Dang it.
So basically what has to happen is that we have to have a mechanism for that excess energy that they have to flow out of the system. So like I can't do this in a Yeti cooler. What's the whole point of like the Yeti drink cups?
Keeps it colder, keeps it warm.
Keeps it cold, keeps it warm. Basically, you're preventing a flow of energy. That's the whole point of Yeti cups.
What is it?
So if you have a hot beverage, the Yeti then prevents that hot from getting cold and losing the energy. If you have a cold drink, it prevents
Energy coming in.
energy coming in. Okay? So Yeti coolers, they want Q to be 0. Because if Q becomes 0, guess what? Change in temperature becomes
0.
and your beverage stays hot or your beverage stays cold.
Oh, what are those things made out of?
Usually it's just aluminum, but it's the insulating material between the inner cup and the outer cup. That's what makes it work. Usually it might even be just like a vacuum, because vacuums don't transmit thermal energy very well. Okay, so what do you know about Q and W? They're the opposite sign, but
They're the same value.
so what if I reverse the process? What's the only thing up here that's going to change? The volumes, instead of having 0.5 or 0.05 over 0.1, I'm going to have 0.01 over. What's going to happen to the sign of work? It's going to be negative. So that means I'm going to dump energy into the system, but the volume's going to get bigger. So this one I'm taking energy out of the system, but the volume's getting smaller. Okay. Now, at this point, I'm going to take this line across. Okay? work being done?
No.
Yes.
Change volume.
Is the volume changing?
Yes.
Yes. Is the volume getting bigger?
Oh.
Yes.
Yes.
The volume's getting bigger is a sign of work, positive or negative. Because it's costing the system energy.
Yes.
Okay? It's costing it energy. So when you have a horizontal line, and this looks surprisingly like a rectangle, we're going to use the idea that work equals negative P delta V. Now, I don't care what the numbers are. I don't care.
Literally. No care.
But I got negative P. Now, this is going to be V minus V naught. Clearly, which is bigger? I'm starting at 0.01 and I'm ending up at 0.05. So which one's bigger? The final is, right?
Yep.
So this number in here is going to be a positive value. Positive value multiplied by negative pressure gives me negative work, which matches with the... Caroline, you're quite excited about
I
this.
am, I understand it. So
Okay.
yes.
So this is going to be negative work because the volume is getting bigger. Yes?
Okay, so I see where you're getting all of these equations, but are you going to give these ones to us on the test?
Look, okay, the only equation that's not up here is this. Every other equation is on the back of your equation
The
sheet.
work
Like, are you gonna
equation you're asking.
Are you gonna pull it on of here?
If you look on the back of your sheet, there's one that says work equals negative P delta V.
Zoom in. Your special effects.
The only one that isn't here is this one, and I said, I will give you that equation. Now, let's talk temperature.
Okay.
This temperature here is 300. Is it Toby?
Yes, Toby.
Toby, you're blushing.
Chilling.
I've been chilling back. I said it's getting hot. We're talking about temperature.
All aflutter?
All of
Trying to get me in trouble. I was like, what?
You don't need any help getting you in trouble. You're fine. Fine
myself?
job of doing that by yourself. Okay, so here's the question. Is this temperature over here going to be bigger or smaller or equal to 300? What's this?
I don't know. You don't too?
Really?
No.
Really?
Hold on.
No.
Even an option.
No, all right.
The answer C. I choose C. PV equals N R P.
As you go across, what happens to the volume? It increases. What happens to the pressure? Love of God! What happens to the pressure? Nothing! What happens to nerve? So if the volume gets bigger, the temperature has to get bigger. Okay? It stays the same.
Hey man, I just want to live in this nice world that's always the same temperature.
You gotta blur that.
Okay. So, as we go across, I'm going to increase the temperature. But the pressure is going to stay the same. Now, this is a vital conceptual thing that you have to understand about what's happening in this process. Okay? So, imagine that you have a classroom, here's your second grade classroom full of Timmies, right? And there are pressure sensors in the walls that are directly reported back to the office. Okay? And what these pressure sensors do is that they respond to Timmies that are running into the wall. And that's going to correspond to a certain pressure. Okay? Now, here's what's happening. We're going to make the room bigger. Now, if we just made the room bigger and did nothing to the temperature, if we just made the room bigger, what do you think would happen to the pressure?
Decrease.
It would decrease. Why?
Because the molecules are further apart.
Yeah, you're not going to have as many collisions. But that's assuming that the Timmies in the world still have the same kinetic energy. But that's not what's happening. We're making the room bigger, right? But what's happening to the temperature? Temperature's going up. So instead of Timmy hitting at 300, Timmy's going to be hitting at like 500, right? So we're going to compensate for the smaller number of collisions, but they're going to have more kinetic energy. So the pressure is going to stay the same. So the principal won't even know what's happening. The principal is going to walk in and go, whoa, what happened to the size of my classroom? The pressure didn't change. And the Timmies in the world are going, wow, I am so strung out on hot chocolate and marshmallows right now, I can't even see straight. Right? So, I mean, they're going into withdrawal. I mean, they're holding up signs on street corners on the weekends going, hey, you know, kinetic energy in search of chocolate, man. So, it's like a obelisk person. So, this is how we can do it, is that we make the room bigger, but at the same time we increase the kinetic energy. Now, the temperature is going to go up. So what's the sign of delta U? Positive, right? Positive delta U. Now, here's one of the most important things that you have to look at. I got a positive delta U, but I've got negative work. So, my Q has to be positive and bigger. So I've got to dump more energy into the system than what it costs me in work. Okay? So, I've got to have a big positive Q. Now, if I reverse this, what's going to happen? Yeah, I'm going to have positive work and a negative Q to produce a negative delta U. Okay. Now, at this point, I'm here. I could go down with this. Okay? A little bit. But as soon as I have a vertical line, that means I am isometric or isovolumetric. It's the same thing. So, think about this. Okay? So, if you visualize what's happening from here to here, right? So, what's happening is this. I've got a small volume, and I want to go to a big volume. So, this plunger is going to go up, right? And I'm doing that by dumping thermal energy into the system. Maybe I throw it into a hot water bath. I do something. So I dump a bunch of energy into the system, and that plunger is going to go up. Okay? So, at this point, I'm at some temperature. But now, think about what has to happen. I'm going to keep the same volume, so the classroom is going to stay the same size. Okay? But I want the pressures sensors to record a lower number. So the temperature has to go smaller. Okay? So what's going to happen to the little Timmies in the world? They're going to get tired. Okay? So we strung Timmy out and got him hooked on hot chocolate with little marshmallows. You know, the little Swiss packets. You know exactly what I'm talking about. Okay? Right? Money. Right? But so we create this addict, right? And then we have to go into withdrawal. Okay? Okay? And so now Timmy's going, what? We don't get any more hot chocolate, okay? And he kind of starts to, you know, he starts to settle in the corner, sucking his thumb in the fetal position at this point, okay? All right. Sorry, Carol.
I'm just picturing this.
And this is why I can't teach at like middle school level, because I can't do this, and I could, but they'd go home and tell mom that they're talking, Mr. Burkamp's talking about second graders strung out on hot chocolate. What does this mean? Yeah, what is withdrawal?
Right.
He's doing this in class. I don't know what it means. Okay.
Joker right now.
Huh?
I'm feeling like the Joker right now.
Okay. All right. That's cool.
Use the card.
So, on the review, to give you some indication of how complex this problem is, on the review, problem number 2, there's only 9. Problem number 2 goes A through O.
Oh my goodness.
Okay? It's all one big problem. So,
That's how
Okay, I'm rethinking my life.
yeah. So when you, this is literally, if you work nothing else, you make sure you can work problem number 2. And then you work it again, and then you work it again.
I'm
Until
gonna have to
2 o'clock in the
answer
morning and you're like,
this question.
You're like Timmy?
yeah, you're like Timmy, I need a hot chocolate.
Yeah. What do you
Go to
need?
the store.
Or better yet, you can just give me the hot chocolate. It doesn't have the marshmallows in it. And then he's like, okay. So, Katie, stop the camera. We're done.
So.